Hi, and welcome back. Today we're going to be discussing nuclear magnetic resonance spectroscopy, which is chapter 16 in versions 1 and 2 of Klein, and chapter 15 in version 3. So, what is NMR spectroscopy? So I'm going to be pretty brief in discussing this background material because I want to focus more on interpretation of spectra. So, nuclear magnetic resonance spectroscopy is a very powerful method in determining the structure of your compound. So if we couple NMR with GCMS and IR, we can usually definitively determine the structure of small organic molecules. It gets a little more complicated if we're trying to do something like a protein, and there are techniques for that. But for small molecules, like drug molecules, NMR is a very powerful technique. So we're going to be discussing proton NMR, which means we're going to be looking at the hydrogens in a molecule. And at the end of the chapter, we'll discuss carbon-13 NMR, which looks at an isotope of carbon, so we can determine information about the carbons in our molecule. And we'll discuss that at the end of the chapter, probably in a separate video. So the connectivity of a molecule affects how radiation interacts with that molecule, and that connectivity can give us information about the molecule's structure. So protons and neutrons in a nucleus have what's called a spin. So they actually aren't sitting still, they're actually spinning. And normally with spectroscopy, we're looking at the electrons in a molecule, but NMR is dealing with the nucleus of a molecule. So if the nucleus has an odd number of nuclei, or protons and neutrons, then it will have a net nuclear spin. So we can actually perform NMR on hydrogens, which is called proton NMR, carbon-13, which is carbon-13 NMR, and also some isotopes of nitrogen, fluorine, and phosphorus, for example. We'll only be looking at proton and carbon-13 NMR in this class. So spinning charged particles create a magnetic field, and because they have a magnetic field, they can interact with an external magnetic field, and we can get some information from that. So these nuclei will align themselves with an external magnetic field, either in the direction of the field or opposed to the direction of the field. And so if you apply so these nuclei are actually going in all different directions, and if you apply an external magnetic field, some of the nuclei will align themselves with the field, that would be the alpha state, and some of them will align themselves against the field, and that'll be the beta state. More are going to be aligned with the field than against the field, because against the field is higher energy. But that's what actually gives us our signal. So we're going to watch these nuclei that are aligned against the field as they relax, and we'll get information from that. So there's a certain energy gap between that alpha and beta spin state being aligned with and against the field, and that energy gap is going to give us some information about that molecule. So that if you have a stronger magnetic field, it's going to be a greater energy gap, and it turns out that we can actually get more information if we have a stronger magnet. All right, and so the more shielded an electron is, it's going to affect how it interacts with that field. So if we have more nuclei around it, or if we have more electrons around it, we're going to see a difference in how it interacts with the external field. So the more shielded a nucleus is, with the electron density around it, the smaller the energy gap, and that's going to affect where these nuclei end up in the spectrum. So we're actually going to bombard these nuclei with radio frequency energy, and when the alpha spins are flipped to beta, the atoms are said to be in resonance. Sorry about that. And so the term resonance here doesn't mean like resonance in as we talk about like a carbonyl with a double bond. We're not talking about moving pi electrons. We're talking about being in resonance with the external field and how that affects the way that it interacts with that field. Okay. So we use a magnetic field and radio frequency energy. So we bombard that molecule with radio frequency energy in the presence of that magnetic field. And again, it can align with the field or against the field. And the larger the magnetic field, the larger the energy gap. Now, an NMR is a big magnet that is at 4 degrees Kelvin, and that magnet is held in superconducting material. Is a superconducting material, that's held in liquid helium in order to keep it at 4 degrees Kelvin. And so by keeping that magnet cold, it actually maintains its charge, and it will actually continue to conduct electricity, which will continue to produce the magnetic field. All right, and so what we do is bombard. So inside the magnetic field, we bombard the sample with that radio frequency pulse, and then we get all of the information at the same time from the sample that is interpreted as a Fourier transform NMR. And so the computer interprets that signal for us and gives us the information for the sample. So the sample is placed into a magnetic field in a tube that's placed inside the instrument. And so that tube is spun at a high rate inside the instrument. We bombard it with the radio frequency radiation, and that's how we get our information. So here's what an NMR looks like. Our tube goes right down in the center of the NMR. We bombard it with radio frequency radiation, and that gives us a signal as the samples are flipped against the field and then come back down to just a normal state. So we're receiving that information as they relax. So generally we use deuterated solvents, so we have a deuterium instead of a hydrogen on our solvents in order to not interfere with the signal. Okay. So also we'll talk about in a minute, we use an internal standard called TMS that allows us to set our zero mark or calibrate our sample against the spectrum. So here are the pieces of information that we get from a spectrum. It's a little more complicated or a little more challenging to interpret an NMR than it is, say, an IR. And so, because we have so many different pieces of information, the first thing we have is the number of signals, and that tells us how many different types of hydrogens we have in the molecule. So even though we have a lot of peaks here, this spectrum only has 3 signals. So this signal here at about 1.3 ppm. So right here, let me go ahead and mark that. This signal here at about 2.6 ppm, that's another signal. And then we have a signal just above 7. So we have 3 signals in this spectrum. That's our number of signals. The signal location is also going to give us some information. That's called our chemical shift. We have this one here at about 1.3, this one here at about 2.6, and this one here at about 7.3. The signal area, or the area under the peak, is going to give us some information about that signal. That's going to tell us how many hydrogens are associated with that signal. And then we have the signal shape, or the splitting pattern. For example, this one is split into 3 peaks. This one is split into 4 peaks. And this one is split into a multiplet. So we're going to get some information also from the splitting pattern. So all of these pieces of information we're going to put together to determine the structure of our molecule. So first of all, we're going to talk about the number of signals. So hydrogens with different electronic environment give different signals. Hydrogens that are homotopic, meaning they're equivalent, will have perfectly overlapping signals. Hydrogens that are homotopic if the molecule has an axis of rotational symmetry that allows one proton or hydrogen to be rotated onto the other without changing the molecule. In other words, these are equivalent because if we rotate the molecule about an axis that exists here, then this hydrogen would be we wouldn't be able to tell these 2 hydrogens apart, right? And these hydrogens, if we call this HA and this HB, they're equivalent because if we rotate about an axis here, then we can't tell HA from HB. If we flip it over, let's say we flip the molecule over, we can't tell HA, from HB. All right? And I don't know how to get that to go away. Okay, and these two hydrogens, let's call them HA and HB. If we rotate this molecule about this axis, then we can't tell HA from HB. So another test to determine if they're homotopic or if they're equivalent is to replace one of them with something else. So we're replacing one of these hydrogens with a deuterium, and we flip the molecule over, and we can't tell, the difference between the two. So these two would be the same compound. If replacement gives us the same compound, because we can flip them over on top of each other and they would be the same, they would be identical compounds, then those hydrogens are homotopic. So we call hydrogens in NMR, we call them protons. So these protons are enantiotopic if they also have perfectly overlapping signals. So let me say, if they're homotopic, they're going to give you the same signal. You're not going to be able to see a difference in NMR. Also, if they're enantiotopic, they're going to give you the same signal. You're not going to see a difference in NMR. So protons are enantiotopic if they have a plane of reflection that makes one a mirror image of the other. So instead of an axis, we're looking at a plane. So if one half of the molecule is a mirror image of the other, in other words, this fluorine and this chlorine, if I cut them in half and draw a mirror plane right down the middle of the half of each molecule, of each atom, then I can reflect the right half onto the left half and vice versa. So this molecule has a plane that splits it down the center, making hydrogen A and hydrogen B enantiotopic. The same is actually true with this molecule. It's a little harder to see. HA and HB are equivalent because there's a mirror plane that slices right down the center of this molecule. So I'm slicing, let me draw some different colors here. Right down through the center of those atoms I've highlighted in red in order to have a mirror plane that slices that molecule in half right down the center of those atoms. So that's a little bit more challenging to observe the mirror plane in that molecule, but these hydrogens A and B are also enantiotopic, so they're going to give you the same signal in NMR. So in other words, if I replace one of these hydrogens with a deuterium, would I be able to flip that molecule around on top of itself and see that that is the same molecule? Or would I be able to flip it around on top of itself and see if if I would be able to put a mirror in between them and see if I have enantiomers. So that's what's true in this case. I can put a mirror between them, and I see that these are enantiomers of each other from that replacement test, and therefore these hydrogens, let's call them HA and HB, are going to give us the same signal in NMR. Okay, so HA and HB over here on the left are going to give us the same signal because they are enantiotopic. So if the protons are neither homotopic nor enantiotopic, then they're not chemically equivalent, and they're going to give us different signals in NMR. In other words, these are, if they're just completely different, or in this case, if they're diastereotopic. So in this case, we have diastereotopic hydrogens because if you replaced one of these hydrogens with something like a deuterium, you've created a chiral center, okay? Or maybe if we replace it even with a chlorine, what have we done? We've created a new chiral center because we have 4 different things attached here. Let's observe. This carbon has 1, 2, 3 things attached plus the rest of the molecule, so that's 4. And notice that we also have another chiral center here. So, and that chiral center has 1, 2, 3, and the rest of the molecule, 4 different things attached. If you have 2 different chiral centers, then what do you have? You can have diastereomers. So these hydrogens, if you replace them with something like a deuterium or even say a chlorine, you can see that we form diastereomers Okay, and so these two molecules would be diastereomers to each other because we have different arrangements at those chiral carbons. In other words, one of them is still coming out on the first one, and the second one, one's coming out and one's going back, making them diastereomers. And therefore, these are diastereotopic hydrogens. If the hydrogens by replacement can create a diastereomer, then they are diastereotopic. And the thing is, diastereotopic hydrogens are not chemically equivalent and will give you a different signal in NMR. Now, in this class, we're not going to have a lot of time to discuss diastereotopic hydrogens. I'm not going to emphasize that too much in depth, but I will discuss it just a little bit. All right, so let's consider some of these shortcuts we can take to determine how many signals we'll have. So we're going to talk about how many signals we'll have in NMR. So before we move on, let me just give you a little example here. So let's say we had this molecule. Everybody should know what this molecule is. This is acetone. How many signals do you think we would have in NMR for acetone? Well, these three hydrogens are all equivalent to each other because if we rotate about this carbon, so we could rotate between these two carbons about this axis, we can't tell HA, HB, and HC apart. We can't tell which is which. And then over here on the other side of the molecule, okay, we have three more hydrogens, so let's call them D, E, and F. And we can't tell D from E from F. But notice that if we actually rotate the molecule this way, if we spin it about that axis right down the center, then we can't tell H, A, B, and C from D, E, and F. So it turns out in NMR, all 6 of these hydrogens are going to give us one signal. We'll only have one signal in NMR for acetone. All 6 hydrogens will give us one signal. Okay? Because we can rotate about the axis and they will be all equivalent. So if you can't tell them apart, if you can rotate about an axis and you can't tell them apart, then they're equivalent. So also, if you have a plane that you can reflect across, then they're equivalent. So let's look for that plane here in this molecule. So if we draw a plane right down in the plane of the board, down the center of this molecule, in the plane of the board, you can see that these two hydrogens, HA and HB, are equivalent. Because going this way, they have the same thing on the molecule. Going this way, they have the same thing on the molecule. There's a plane of symmetry right down the plane of the board, or the plane of the paper. Now, if I put an OH group here, like on the molecule on the right, now I've created diastereotopic hydrogens because replacing them with something like a chlorine would potentially give me a set of diastereomers. And because I can create diastereomers that way, these are not chemically equivalent. So they're going to give me a different signal. So let me erase this and let's just consider some other pieces of this molecule. So also we have 2 hydrogens on this carbon, and they're going to give us a different signal as well. And of course we've got another hydrogen here. So we're going to see signals for all of those hydrogens and the hydrogen on the oxygen and the hydrogens on the benzene ring. But just getting back to the point of this slide, these 2 hydrogens are not equivalent because they create a diastereotopic center because this OH group is present. Alright, so moving on, the 3 hydrogens on any methyl group will always be equivalent to each other because you can rotate around that methyl group. You can rotate a methyl group around to its neighbor, to its neighboring carbon, and all 3 of these hydrogens will be equivalent to each other. Alright, and multiple hydrogens are equivalent, like we talked about with acetone, if they can be exchanged through either a rotation or a mirror plane. So like this molecule here, I have diethyl ketone, then, or I have 3-pentanone, they're called the same thing. Then these 4 hydrogens are equivalent because if I rotate around, I would have the same molecule. Okay, and also notice that these 3 hydrogens are equivalent to each other, and they're also equivalent to these 3 hydrogens over here. So I'm going to get 1 signal for all 6 of these hydrogens, and I'm going to get 1 signal for all 4 of these hydrogens. Alright, so let's see if we can determine the number of signals expected in a proton NMR spectrum for each one of the following compounds. So let's look at A first. Okay, so I have, let me redraw the molecule over here. Now, this is a CH3, that OMe. You should know that by now. Alright, and this is a CH2, CH3, CH2, CH3. Okay, and so these 2 hydrogens are equivalent to each other because we have a plane of symmetry right down the plane of the paper. These 3 hydrogens are equivalent to each other because they're a methyl group. These 3 are equivalent to each other. These 2 are equivalent because there's a plane of symmetry down the center of the paper. Okay, these 3 are equivalent to each other. And this one, and this one, and this one are all different from each other. So how many signals would we have? Now these 3 are not equivalent. Let me get another color here. These 3 are not equivalent to these 3. Why? Because this ethyl group on the left is only 1 carbon away from this methoxy group. And this ethyl group on the right is 2 carbons away. So they're not equivalent to each other. So that means we're going to have 1, 2. This CH2 is not equivalent to this CH2. 1, 2 for these CH2, 3 for this CH3, 4 for this hydrogen, 5 for this CH3, 6, 7, 8. 8 signals in NMR. Okay, let's look at B. So we have a benzene ring, a methyl group, and an OCH3. So remember, methyl groups, all 3 of those are equivalent to each other. Here, this methyl group, all 3 of these are equivalent to each other. They're not equivalent, the methyl groups are not equivalent to each other though. So we're going to get 1 signal for this CH3 and another signal for this CH3. Now we have a hydrogen here, hydrogen here, hydrogen here, hydrogen here. So that gives us 1, 2, 3, 4, 5, 6 signals. Let's move on to C. Now C, notice, has a lot of symmetry, rotational symmetry. So it turns out, and reflectional symmetry. So I have, if I consider I have a rotational axis right there, then that makes HA and HB equivalent to each other. And also HC and HD would be equivalent to each other. And of course, if I call this one E and this one F, all of E are equivalent to themselves and all of F are equivalent to themselves. But notice I also have an axis, let me get a different color, going this way, right down the center of the molecule. So if I flip across that axis, then hydrogens on F are equivalent to those on E. So E is equivalent to F, and that makes B equivalent to D, and A equivalent to C. So it turns out I'm only going to have 1 signal for A, B, C, and D, and 1 signal for E and F. So I'm going to get 2 signals in the NMR for that molecule. For that whole molecule is only going to have 2 signals. Now let's look at D. I have 2 methyl groups. These are now on the side. I do have a plane of symmetry right down the center of this molecule, okay? So that means that I can reflect across that plane, making the hydrogens on A equivalent to the hydrogens on B. And if I call these C and D, then they are equivalent to each other across that plane. And E and F are going to be equivalent to each other across that plane. But C and D are not equivalent to E and F because C and D are 1 carbon away from the methyl group, and E and F are 2 carbons away from the methyl group. So that's going to give me 1, 2, 3, 4, 5, 6 signals in NMR. And that leaves us with one problem, and that is E. Now, there are a few more in your book for you to practice, okay? All right, so I've got the methyl groups are all the three are equivalent to each other. And now I have, let's call these A, B, C, D, and E. So let me grab a different color. Now, the methyls are equivalent to each other, so that's one signal. D, okay, but do we have a plane of symmetry here? No, we don't, because this methyl is not going to reflect onto that chlorine and give us the same thing. So A, B, C, and D are all different. So that's 2, 3, 4, and 5. Of course, we don't get a signal for the chlorine because this is not chlorine NMR. This is proton NMR. All right, and so here's an interesting case. Cyclohexane chairs have 6 equitorial. They didn't spell that right, did they? 6 equitorial and 6 axial protons. And so if you could hold them at a very low temperature where they would stay in that chair conformation, you could in fact get 2 signals. All of the axial protons are equivalent to all the other axial protons. They're all equivalent to each other. And the equatorial protons are all equivalent to each other. You could get 2 signals. But since they remember, flip back and forth from axial to equatorial, it turns out in NMR at room temperature, we only get 1 signal in NMR for all of the protons that are on the cyclohexane molecule. Okay, so TMS is our tetramethylsilane. This is used as an internal standard for NMR. And so what we do is we add about 1% TMS to the sample, and when we take the NMR, we're going to set that TMS signal to 0. And that's because this silicon actually pushes electron density onto the methyl groups, shields them to the point that these hydrogens are more shielded and they're going to come in at 0. Now, we're going to talk about what that shielding means to our chemical shift in just the next section, but just know that TMS sets our signal. We set that signal to 0 as our internal standard. And the signal is calculated relative to TMS as the observed shift from TMS in hertz divided by the operating frequency of the instrument. So the observed shift times 10 to the 6 over the operating frequency, which is going to give us our signal in a unit called parts per million, which really doesn't have anything to do with concentration. What it has to do with is this 10 to the 6 right here, because it's 10 to the 6, it's to the million, so that's why it's called parts per million. But if the signal is going to be standardized in this way so that you'll get the same chemical shift no matter what the operating signal is, the operating frequency is of your instrument. You're always going to get the same chemical shift, which is convenient for instrument to instrument, and that's why this notation is used. Okay, so benzene comes in at around 7 relative to TMS. So that's our next section that we're going to talk about is chemical shift. So our spectrum goes, remember we talked about number of signals, so now we're talking about chemical shift. The chemical shift is where those signals end up in the spectrum. So our spectrum goes from about 0 all the way up to maybe 12 ppm or parts per million. Okay, so very few things actually will show up at 12. An aldehyde is at 10. Carboxylic acid is at 12. But the way that we consider chemical shift is we have we call these signals here toward the 0 end upfield, and we call the signals here toward the 10 end downfield. And that has to do with the way the original instruments were calibrated, and you actually had to turn a dial to get them to change. And so, but now we take all of the signals at the same time. So this area toward 0 is upfield, and this area toward the other end is downfield. So shielded protons require a stronger external magnet back in the day, and so that's why they were called upfield and the others were downfield. But today it's the opposite, because the shielded protons have a smaller magnetic force acting on them, so they have smaller energy gaps and absorb lower energy radio waves. We actually have lower energy upfield and higher energy downfield. But that's kind of irrelevant. What we're going to do is look at chemical shift tables in order to determine where our sample is going to end up on the spectrum. Okay, just know that our spectrum goes from 0 to about 12 ppm, and we're going to look at how they fall on that chart according to what our hydrogens are attached to or what type of environment they're in. So alkane protons generally give signals around 1 to 2 or maybe 0.8 or so to about 2 ppm. Okay, so those are upfield. So they can be shifted downfield when a nearby electronegative atom causes deshielding. So they're shielded by the electrons that are around them. And if you have an electronegative atom, that's going to deshield those hydrogens. Okay, so a regular alkane is around 1. If you put, say, an iodine on there, you know iodine is electronegative. That's going to withdraw electron density. So the hydrogens that are directly attached to the carbon bearing the iodine are going to come in at around 2.2. So we're adding about 1.2 ppm per iodine to that carbon, okay? So the hydrogens that are attached to a carbon bearing a bromine are going to be at around 2.7. Remember, fluorine is the most electronegative element on the periodic table, so it's going to give us a higher deshielding, okay? So if we have 1 chlorine, the hydrogens that are attached to the carbon bearing the chlorine are going to come in at about 3.1. So notice that's about 2.1 added to relative to the alkane for the chlorine. And then if we have a fluorine, they're going to see those hydrogens attached to the carbon bearing the fluorine at about 4.3. So we've added about 3.3 from that fluorine. So notice that this effect is in fact additive. So if we have a carbon bearing 1 chlorine, for example, we're going to see it at about 3.1. So we've added about 2.1 to those hydrogens that are attached to the carbon bearing the chlorine for that chlorine, right? So notice that if we put 2 chlorines on that carbon, then these hydrogens that are still attached, we only have 2 of them now, are going to be at about 5.5. So we've added about another 2.1 or so, okay, to the chemical shift. If we add 3 chlorines, then that 1 hydrogen that's left is going to show up around 7.3. So we've added about another 2.1 or so to that chemical shift, okay, to the carbon directly attached to the chlorines. So that we're talking about the hydrogen that's directly attached to the carbon bearing the chlorines. Now, as we move away from that carbon that's bearing the chlorines, we call that the alpha carbon, the beta and the gamma carbon is going to see a slight shift. So the beta carbon, we're going to see these hydrogens coming in at about 1.6, and then we really don't see a difference with the gamma hydrogens on the gamma carbon because they're so far away from that chlorine. We're not going to see that inductive effect very strongly through the bonds. So we're talking about an inductive effect from having those electron withdrawing elements on the atoms bearing the hydrogens or maybe on the atoms next door. Now you see that this is additive. For every chlorine that we have on here, we're going to add about 2.1 ppm to the chemical shift. And the same is true for, say, the iodine and the bromine. So for the iodine, we added about 1.2, so we're going to add about 1.2 for each iodine. And for the bromine, we added about 1.7, so we're going to add 1.7 to the hydrogens on that carbon bearing the bromine for each bromine. Obviously, if we have 4 chlorines, 4 iodines, or 4 bromines, or 4 fluorines on the carbon, then we're not going to have any hydrogens on it. So if you don't have any hydrogens, you're not going to see a signal. This is proton NMR, right? Another thing to note is that here at about 7 Okay, we don't see very many peaks around the 7 region, except for something on a benzene ring. That's where we're going to see signals from hydrogens that are on a benzene ring. We're going to see those at around 7. So we can even drag those down into the aromatic region and maybe even have some confusion there because we only expect to see aromatic hydrogens around 7. But just keep that in mind for when we come to that. So there's a difference between, say, a methyl versus a methylene versus a methine group at about 0.9, 1.2, and 1.7, okay? But it's really difficult to tell the difference in these. Honestly, just remember an alkyl group comes in at around 1. Okay, now if you have a carbon that's bearing an OH, the hydrogens that are also on that carbon, okay, notice those are going to be adding about 2.5 to the methylene group, and so they're going to come in at about 3.7. If you have carbons next to an oxygen of an ester, you're going to add about 3 ppm, and so those are going to show up at around 4.2 ppm, okay? So if you have hydrogens next to a carbonyl group, you're going to add about 1. It's going to show up at about 2.2. So you can use a chemical shift table or a handbook to determine where your hydrogens are going to show up. I usually just kind of estimate it or guesstimate it or use a little table. It's easy to determine it that way. Okay, so let's see if we can predict the chemical shift for all of the hydrogens in this molecule. So there are no hydrogens on that carbon, so let's just start with him. So notice that guy has no hydrogen, so we're not going to get a signal in proton NMR for him. Now we will see a signal in carbon NMR. Okay, carbon 13 NMR. Well, let's look at this carbon. This carbon has 2 hydrogens. Okay, so where are those hydrogens going to show up? Well, they're next door to this carbon bearing the chlorines. Notice the carbon that has the chlorines on it. That carbon has 0 hydrogens, okay? So these carbons, these are at the beta position. So let's go back up here and take a look and see, if we can figure that out. Okay, so we're talking about these hydrogens at the beta position next to a chlorine, and that's 2 chlorines. So that's going to come in at about 1.6 if you have 1 chlorine. Now we have 3 chlorines, so we're adding about 0.6 per chlorine, according to that chart. So 0.6 times 3 is 2.8. So we're going to add 2.8 plus 1 for the alkyl group. So that's going to be at about 3.8. Okay, so these hydrogens are going to come in at about 3.8. This OH, hydrogen on an OH can come anywhere from 2 to about 5 ppm. They do vary quite a bit. A hydrogen next to a carbonyl is about 3.5 or 3.7, something like that. And it's also got this OH next door, so it might even be further down. And this methyl group here, about 1.5 to 2, because it's next to this carbon bearing an oxygen. So this is kind of approximate, but just kind of get an idea of the region we would see these signals. Now, talking about the aromatic system, we see those at around 7 because they're deshielded due to this diamagnetic anisotropy. And that's because of this, what's called a ring current. So that's also called a ring current that actually exists in the benzene ring. Okay, and so the hydrogens that are on the benzene ring stick out from that circulating current that's on the ring, and I've drawn too many hydrogens on there, but anyway. So since they stick out, they are deshielded by that effect, and so that's going to make the hydrogens that are on a benzene ring, just know they come in at around 7. Sometimes you'll see them at around 8 if you have some more electron withdrawing groups on the ring. But they usually show up in the 7 region. So notice that we have 5 hydrogens on this benzene ring, this ethyl benzene, and so all of those are going to show up in the 7 region as a multiplet. So we're going to look at what the shape of the signals in just a minute. Okay. So all of these show up around 7. And then we have these other hydrogens, the CH2 and the CH3. And the CH2 is actually closer to the benzene ring, so it's a little more deshielded. It's going to show up about 2.5. And the CH3 is going to show up at around 1. So I have 1, 2, 3 signals in this NMR. Now we're seeing a signal as a multiplet for all of these because it's different to tell the difference between them. But some instruments are powerful enough that we can blow that up and get a different signal for these hydrogens. We actually would have 1, 2, 3 signals for those hydrogens on the benzene ring, but sometimes we can't distinguish between those because we don't have good enough resolution, and so we'll see just a multiplet on that benzene ring. Sometimes we can see differences between them. So we really would expect 3 signals for the hydrogens on the benzene ring, and then the CH2 would be 4 and the CH3 would be 5. So we would have 5 signals in the spectrum, but since they're so close together, they're on top of each other, we end up with a multiplet. Now, if you have a really large molecule like this 14-annuline that is aromatic, these hydrogens that are in the center are going to show up. They're more shielded because of that ring current, because of that diamagnetic anisotropy. So because they're more shielded, they're going to be even lower, even more upfield than TMS, and they're going to come in at -1 ppm. We generally don't see a lot of hydrogens in proton NMR that are below TMS, but sometimes it can happen. And the other hydrogens would be at around 7. Or in this case, 8, I'm sorry. So here's where we see some chemical shifts. I usually just use a table like this. So a methyl group is going to be at around 1, methylene 2. 1.2. A methine, meaning we have a carbon with just 1 hydrogen and 3 alkyl groups, is 1.7. Allylic is about 2. Alkynyl, 2.5. An aromatic methyl, so next to a benzene ring, at about 2.5. An alkyl halide, 2 to 4. An alcohol, 2 to 5, and that's the hydrogen on the alcohol, okay? Vinylic, 4 to 6. Aryl, 6.5 to 8, so something on a benzene ring. An aldehyde is about 10, and a carboxylic acid is about 12. That makes these aldehyde and carboxylic acid hydrogens very specific. If you see a hydrogen at 10, you've got an aldehyde. If you see a hydrogen at 12, you've got a carboxylic acid. It's very specific for those groups. So let's try to predict the chemical shifts for these here. And I'm just going to kind of come up with this off the top of my head. I'm really not too concerned about it. So next to this oxygen, we've got a little bit of de-shielding. So these 2 hydrogens here are going to be about 2.5. This is pretty far away from the oxygen. It's a CH2, so about 1.5. And this one's going to be about 1. Here we've got next to a carbonyl. I don't remember. Those were around 2.5, I think. And this one's at about 1. Okay. So next to an oxygen, around 2.5. No hydrogens here. This is far enough away from the oxygen, maybe about 1, both of those methyl groups. Okay, we've got a CH there, so that's about 1.7. CH3s are about 1. This next to an aldehyde is around 2.5, I think, and around 2.5. So you can look these up on a table to get a little bit more specific, but I think you get the idea. Oxygen is electronegative, and it's going to withdraw electron density through induction, and therefore moves things down if they're next door to an oxygen, not on the same carbon, to around 2.5. Okay. So the integration is the next thing. So we talked about number of signals. We talked about chemical shift. So now we're going to talk about integration. Okay, so this is the next piece of information that we're going to have, and it's very powerful because it tells us how many hydrogens are associated with each signal. So the older computers used to give us a big plotter, and they actually gave us what's called these step curves, and we would actually have to measure them with a ruler to determine how many hydrogens were associated with each signal. But the newer computers will actually give you a number under the curve, and that is a ratio of how many hydrogens are in your signals. Okay, and so with that signal, you can see that we have about a 1 to 1 to 1.5 to 1.5 ratio, and these are ratios now to our signal. So that means if we've got a 1 to 1.5 to 1 to 1.5 ratio, of hydrogens associated with those signals. Well, we can't have half a hydrogen, and this is not moles. This is actually atoms in a molecule. And therefore, in order to get an even number, we need to double everything. So we would double everything, and we would call that a 2 to 3 to 2 to 3 ratio. A 2 to 3 to 2 to 3 ratio. Now, even that we may have to double again if we have a lot of symmetry in the molecule. So you may even see so much symmetry that you have to double all those numbers again. But right now we're just talking about, how many are associated with each signal, because our smallest signal is going to be given a number of 1, and everything else is going to be relative to that. All right, so what we did, we adjusted them to give us a whole number ratio, 2 to 3 to 2 to 3. So the integration is a relative quantity rather than an absolute count of hydrogens, and symmetry can affect that integration as well. So here we have 2 hydrogens to 3 hydrogens to 2 hydrogens to 3 hydrogens, right? But these 2 are equivalent to these 2, and these 3 are equivalent to these 3. And therefore, we're going to have 2 signals in the NMR, and those signals are going to have a 2 to 3 ratio. What does that mean? It means in order to get the number of hydrogens that we have associated with our molecule, we're going to have to double it again. That's going to be a 4 to 6 ratio. That's going to give us 4 associated with one signal and 6 associated with the other. So if we didn't know the structure of our molecule, we'd have to have another piece of information in order to determine that, and in this case that would be our molecular formula. If we had a molecular formula for this molecule, we could match it up to how many carbons and hydrogens we had, and we would know that we had in fact 10 hydrogens, and we would have to account for those somewhere. Okay, so in order to calculate the integration, we're given values like this that are associated with that signal, and we divide the smallest signal by 1. The smallest signal here is in fact 27, so we're going to divide that by 1 to give us a whole number ratio. So if we divide every signal by 27, that's going to give us a ratio of the signal. So we're standardizing that smallest signal to 1. So 27 divided by 27 is 1. 40.2 is our next signal, divided by 27 is 1.5. 28.4 divided by 27 is about 1. And 42 divided by 27 is about 1.5. So what does that give us? It gives us a 1 to 1.5 to 1 to 1.5 ratio. Well, we can't have half an atom, so what do we need to do? We need to double it. We're going to double it. That's going to give us a 2 to 3 to 2 to 3 ratio. Okay? All right, so let's look at this next one. We have 3 signals in this NMR. We have 1, 2, 3. Our first signal is 6.3, next signal 19.4, next signal 37.9. So if we divide the 6.3, that's our lowest number. We're going to take our lowest number, we're going to divide that by itself, and that's going to give us our ratio, ratio of 1, and then everything else is going to be relative to that, okay? So 6.33 divided by 6.33 is 1, 19.4 divided by 6.33 is 3, 37.9 divided by 6.33 is 6. That gives us a 1 to 3 to 6 ratio of hydrogen. So what does that mean? This signal has 1 hydrogen associated with it. This next signal has 3 hydrogens associated. The next signal has 6 hydrogens associated with it. Or we may need to double that. It may be 1 to 6 to 12. Likely, this is the actual number that we have. And so in the older systems, we'd have these little step charts, and what they would be, this one would be 1, this one would be 3 times as tall as this one would be 6 times as tall as that one, and we would have to actually measure them to get our ratios. But we don't have to do that anymore. We've got these newer systems that give us numbers. Just divide the smallest number, just by everything by the smallest number, and that's going to give you your ratio. All right, so the next topic is multiplicity, and this is probably the most powerful feature of an NMR spectrum. That's the number of peaks associated with each signal. So if a signal is observed, it's often split into multiple peaks in the NMR, and we have these different types of peaks, okay? We have a singlet with 1 peak, a doublet with 2 peaks, a triplet with 3 peaks, a quartet has 4 peaks, a quintet has 5 peaks, a sextet has 6 peaks, and a septet has 7 peaks. Or we may even just see a big blob, and we call that a multiplet. A multiplet, and sometimes we can't tell what that multiplet is. The problem with your book, Klein book, does not really give you good, clear NMR spectra. It's very fuzzy, and sometimes you can't tell what these peaks are supposed to be, and therefore for the ones I've used as examples, I've actually given you that information. Okay? So multiplicity results from each little hydrogen having its own magnetic field and how that magnetic field interacts with the surrounding magnetic field. So spinning charged particles create a magnetic field, and each one of these hydrogens is a spinning charged particle. So if they are next to each other, they're going to affect the other by affecting their magnetic field. So remember that the hydrogens can be aligned with or against the field, and that's going to affect how that's going to affect their individual environment. So HB is going to be aligned with the field in some molecules and against the field in others. Okay, and HA is going to be aligned with the field in some and against the field in others. If HB is aligned with the field, it's going to have a slight shielding effect on HA. If it's aligned against the field, it's going to have a slight de-shielding effect on HA. And that means it's going to either add to or take away from the external field, and that will affect its the signal in the NMR, because remember, we're dividing by the value of the external field in order to get our signal. So it's going to either add to or take away from. So for HA, HB can be aligned with the field or against the field, and that's going to split HA into having 2 possibilities. It'll appear as a doublet because it has, and we're going to look at this in a minute, because it has 1 neighbor, it appears as a doublet. In other words, 1 neighboring hydrogen, 1 hydrogen on a next door carbon. It's going to appear as a doublet. Okay, and that's because for HA, HB could be aligned with the field or against the field, either adding to that external field or taking away from that external field. Now, if HA has 2 neighbors, in that case, both HB protons could be with the field, okay? Both of them could be against the field, okay? And so that would either add to the external magnetic field, which in this case is denoted as B0, or it could take away from the external field, which is B0, either de-shielding or shielding it, either taking it downfield or upfield. Okay, or we could have 1 aligned with the field and 1 aligned against the field, and the other with and the other against. So what does that mean? It means we're going to get a triplet for HA. HA is going to be a triplet in a 1:2:1 ratio. It turns out, because we have this possibility, both with, both against, or 1 with and 1 against in 2 different possibilities, statistically, we're going to have a 1:2:1 ratio for HA. So HA, because it has 2 neighbors, is a triplet. So we're getting to a little rule here. The number of neighbors plus 1 is the number of signals we're going to have for that hydrogen. So it doesn't matter how many hydrogens are associated with the carbon as far as the splitting pattern. It matters how many neighboring hydrogens that carbon has. Okay? So we're going to see a triplet in a 1:2:1 ratio. Now, if HA has 3 neighbors, then they have these different possibilities. All 3 with the field, all 3 against the field, or 2 with, 1 against, 1 with, 2 against. So we could have 3 different possibilities for each of these middle positions, and then all 3 with and all 3 against, giving us 4 different possibilities, 4 different unique possibilities, but statistically we have 3 possibilities each for those 2 center ones. But just know that we get a quartet in a 1:3:3:1 ratio. So if HA has 3 neighbors, 3 neighbors plus 1. We have an n plus 1 rule, where n is the number of neighbors plus 1. We get 4 peaks in that signal in a 1 to 3 to 3 to 1 ratio. Okay? So that gives us a quartet. So here's our chart showing how many peaks we'll have. If the hydrogens have 1 neighbor, we get a doublet. Doesn't matter how many hydrogens are on the carbon we're talking about. How many hydrogens are associated with the signal doesn't tell us how many neighbors it has. Integration tells us that. This is the number of neighbors. So if those hydrogens associated with that signal have 1 neighbor, then that signal is going to be a doublet. It could be 6 hydrogens associated with that signal. The integration could be 6, but if there's a doublet, that means they have 1 neighbor. If the signal is a triplet, then all of the hydrogens associated with that signal have 2 neighbors because of the n plus 1 rule. The n is the number of neighbors. If that signal is a quartet, then you have 3 neighbors because of the n plus 1 rule, where n is the number of neighbors. If we have a sextet, then they have 5 neighbors. If they have a septet, then they have 6 neighbors. And we have these different ratios here. Okay. Now, remember, equivalent protons cannot split one another. So if they're equivalent, then even if they're on neighboring carbons, they don't split each other. Okay? So let's predict the splitting pattern observed by 1,2-dichloroethane. So to split each other, the protons must be within a 2 or 3 bond distance. Okay? So what is going to be the splitting pattern? Well, if they're equivalent, they don't split each other. Okay? So if they're equivalent, that means we're only going to get 1 peak, because equivalent hydrogens don't split each other. So to split each other, they have to be in a 2 or 3 bond distance, but normally we don't see. In other words, they have to be either on the same carbon. Normally, hydrogens that are on the same carbon are not going to split each other unless those are diastereotopic hydrogens. Or they have to be on next door carbons, and if they're next door, then they can split each other. But if they're 2 carbons, if they're like on carbon 1 and carbon 3, they're not going to split each other. They're too far apart. All right, and so let's look at this pattern that we can see, these splitting patterns here. Like a T-butyl group is going to be 9 hydrogens with 1 peak. 1 peak, 9 hydrogens, okay? And so that's a T-butyl group. Very characteristic for a T-butyl group. I mean, it might not be a T-butyl group, but if it quacks like a duck, it's probably a duck, right? Let's look at this isopropyl pattern. So we have 6 hydrogens that are a doublet, and we have 1 hydrogen that has 1, 2, 3, 4, 5, 6, 7 peaks. Okay, so if you have 7 peaks and 2 peaks, what is that going to mean? So we have 6 hydrogens that are a doublet. Why? Because these 6 hydrogens have 1 neighbor. Let's call that neighbor HA. Okay, and these 6 hydrogens have HA for a neighbor, so HA is going to split them into a doublet. They have 1 neighbor according to the n plus 1 rule. And HA has 6 neighbors. We'll call them HB. Okay, so it splits, these 6 neighbors split HB into 7 peaks, because 6 neighbors plus 1 is 7. So that is very characteristic for an isopropyl group. This is an isopropyl group, and it has this characteristic pattern of 1 hydrogen with 7 peaks and 6 hydrogens with 2 peaks. And then here we have an ethyl group. We have 2 hydrogens with 4 peaks, and we have 3 hydrogens with 3 peaks. And that's characteristic of an ethyl group. Why? Because an ethyl group is a CH2, CH3, right? So we have 2 hydrogens here, okay? And they have 3 neighbors. That 3 neighbors is going to split them into 4 peaks. Here we have 3 hydrogens, and they have 2 neighbors. Those 2 neighbors are going to split these 3 hydrogens into 3 peaks. So 2 hydrogens with 4 peaks and 3 hydrogens with 3 peaks is very characteristic for an ethyl group. So below are NMR spectra of several compounds. Let's identify whether these contain an ethyl, an isopropyl, or a T-butyl group. So let's take a look at this. So this molecule right here has 2 peaks with 6 hydrogens, okay? And it has 7 peaks, okay? 1, 2, 3, 4, 5, 6, 7, with 1 hydrogen. So what did that look like? That looked like our isopropyl group. Okay, we can even find out what was in this molecule. We can figure this whole structure out because down here at 7 we have 5 hydrogens. So what's that going to be? 5 hydrogens in the 7 region. That's a benzene ring. So this is in fact the spectrum for an isopropyl group on benzene. Okay, so this one goes to 0 to 8. So this is in the 7 region. That's aromatic. I'm sorry. So next, let's look at the chemical shift on this. Let's look at the next spectrum, and in fact, let's analyze this a little further. So we have 1, 2, 3, 4 signals in this spectrum. So the question is, do we have an ethyl, isopropyl, or T-butyl group? Well, a T-butyl group, remember, has just 1 signal, so we don't have that. And we could have ethyl or isopropyl. All right, and so an isopropyl is two peaks with 6 hydrogens and 7 peaks with 1 hydrogen. So here we have 1, 2, 3, 4, 5, 6, 7 peaks with 1 hydrogen. And here we have 2 peaks with 6 hydrogens, okay? So that means we definitely, in this, I'm going to draw this one a different color here. Okay, let's draw this one in red. So we definitely have an isopropyl group in this molecule, okay? So we have some other things. We have 4 signals in the spectrum. So what other things do we have in the spectrum? Well, we've got a triplet representing 3 hydrogens, okay? And we have a quartet representing 2 hydrogens. What does that look like? Well, that looks like our other pattern here. A quartet with 2 hydrogens, a triplet with 3 hydrogens is an ethyl group, okay? So CH2, CH3, right? So because we have 2 hydrogens with 3 neighbors, that's going to split these 2 hydrogens into 4 peaks. And we have 3 hydrogens right here with 2 neighbors, that's going to split these 3 hydrogens into 3 peaks. Okay, so this is our ethyl group. So we have both things in this spectrum. So those are the only things we have in the spectrum. Let's look at our molecular formula here. C6H12O2, and let's see if we can deduce the structure of this molecule. So we've got 1, 2, 3 carbons in our isopropyl group, and we've also got 7 hydrogens. Okay, our pieces are adding up like this. We've got 2 carbons and 5 hydrogens in our ethyl group. Okay, so that comes to 9 carbons. I'm sorry, I added that up wrong. So that comes to 5 carbons, okay, and 12 hydrogens. All right, and so all of our hydrogens are taken up, because we've got 12 hydrogens in the molecule. We've got 5 carbons taken up. The only thing we have left out, this is C6H12O2. We've got 1 carbon and 2 oxygens left, okay? Let's notice also, so I'm going to go ahead and get the structure of this molecule. You can see how powerful this is. We've got an ethyl group and an isopropyl group and a CO2. Those are what we have. So can we put that together somehow in a way that makes sense? Of course we can. A CO2 is a ester. It's a carboxylic, it's an ester group, okay? And on one side of that ester, we've got to have an isopropyl group. On the other side of the ester, we have, an ethyl group, okay? So, which is which? Can we figure that out? Well, the furthest down is going to be connected to the oxygen, okay? And that's the hydrogen of the isopropyl group, and so therefore this isopropyl group is next to the oxygen, and then on the other side we have to have the ethyl group. So we can actually get the structure of these molecules here. Alright, so the next one in the 7 region, we've got 2 doublets. We got 2 doublets. Okay, let's figure out how many. Let's do this problem, okay? So let's do our integration values. So our lowest one is 6, okay? So 6 divided by 6 is 1. The next one is 12, roughly. 12 divided by 6 is 2. 12 divided by 6 is 2. And then 55 divided by 6 is what? 6 times 10 is 60, right? What's 6 times 9? 54. So that's about 9 hydrogens there, right? So we've got a 1 to 2 or 2 to 2 to 1 to 9 ratio. So what does this thing look like? This looks like a T-butyl group. We've got 9 hydrogens. That's a singlet. That's a T-butyl group. Okay. Notice this little peak here at 5. This is representing 1 hydrogen. Notice how broad it is. They've got us an inset here. You can see how broad it is. That's an OH. That's an OH peak. And then here at 7, we've got these 2 doublets. What does that mean? We have 2 equivalent sets of hydrogens, 2 hydrogens each, on a benzene ring. How do I know that? Because it's in the 7 region. So if we call these HA and these HB, HA and HB are not equivalent to each other. Because if they were, they wouldn't be splitting each other. And so we have this type of connectivity here. So that means that this OH is an end piece and this T-butyl group is an end piece. And if we look at our molecular formula, C10H14O, how many degrees of unsaturation do we have, right? So 2 times 10 is 20 plus 2 is 22. And 22 minus 14 is 8, right? 8 divided by 2 is 4. So we have 4 degrees of unsaturation. That matches a benzene ring exactly. All right, and so we've got 10 carbons. Let's see how many carbons we've used. There's 6 in the ring plus 7, 8, 9, 10. 7, 8, 9, 10. This plus 4 in the T-butyl group. So we've used up all of our carbons. What about our hydrogens? 14. So we've got 4 in the ring plus 9 plus the OH. That's 14 hydrogens. And we've used up the oxygen. So that means we've used all of our pieces here. And so this is our molecule. Okay. So let's do that last molecule. Okay, we've got one more here. And so what do we have? We have 5 in the aromatic region, and that's just a multiplet. But if you have 5, you only can have one thing, a monosubstituted benzene ring, right? Monosubstituted benzene ring. If you have 5 aromatic hydrogens, 1, 2, 3, 4, 5, monosubstituted benzene ring. Now we have something else, so that takes up 6 of our carbons and 5 hydrogens. So that leaves us with 5 hydrogens, 2 carbons, and an oxygen, right? And we've got 3 signals here, so that's interesting. So that means that one of those signals is associated with something that's not on a carbon, probably, because we only have 2 carbons left. So this one is probably an OH, and it's not broad because, remember, an OH can be 2 to 5. This is a little low normally for an OH, but it's not broad because it's probably in some kind of solvent that doesn't allow for the exchange of that hydrogen very well. We'll talk about that in a little bit. And so that gives us a sharper signal. So here we have a triplet and a triplet. So what does that mean? We got two hydrogens with three neighbors. I'm sorry, two hydrogens with two neighbors because it's a triplet, and two hydrogens with two neighbors. So one of these is a CH2 connected to another CH2. So that's CH2, CH2, OH. So that's our molecule. So now the N+1 rule applies to protons that are all equivalent, okay? So if you can have a situation where the hydrogens attached on either side are not equivalent, okay? So we've got a hydrogen here and a hydrogen here, and these are not equivalent. Now, I'm going to discuss this complex splitting, but I'm not really going to work any problems with it because I'm not emphasizing that for my class. But we're going to run through it real quick and just give you an idea if you have some homework problems how you can work those. So what happens here is this hydrogen, if you call this HA, is going to be split into a doublet by HB, okay? And it's going to be split into a doublet by HC. If HA, HB, and HC were equivalent, then it would be a triplet because it has two neighbors. But since HB and HC are not equivalent, then it's going to be split into a doublet by HB and a doublet again by HC. So it's going to be split into a doublet of doublets. And that signal may look like something like this, okay? So you may have one hydrogen associated with a doublet of doublets, for example. I'm not going to work this problem. It's pretty complex. I'm going to just move on. So you see here that HAs are split by the HBs into a triplet. I'm sorry, a quartet. So the HAs are split by the HBs into a quartet, which is a little bit confusing here because they've changed the colors on us. And the HBs are split by HA into a triplet. Notice that the distance between these peaks is the same. The distance between the peaks is the same, and that's called the coupling constant. So we use J for the coupling constant. And J from A to B is the distance between those peaks. So if they are splitting each other, then they're going to have the same coupling constant. So if you say the same distance between the peaks, then that generally indicates that those are splitting each other. Okay, so that's the same distance in hertz. And when they're splitting each other, their coupling constants will be equal. So higher field instruments, stronger instruments are going to give you better resolution. And that's going to give you better ability to tell if your coupling constants are the same. Okay. So if they have different coupling constants, even if it looks like an ethyl group, it may not be an ethyl group because if they are different distances apart, then you can tell that's not an ethyl group. That's not coupled to each other. So a peak with an integration of 9 suggests a T-butyl group, and an isolated isopropyl group gives a doublet and a septet, and these guys are going to have the same coupling constant if you blow them up. Now, so let's look at HB here in blue. It's going to be split into a triplet by HC, okay, and into a quartet by HA. And since you have this X here, it's going to change the environment of HC and HA enough that the coupling constant is going to be vastly different. And so what that means is we're going to have a quartet of triplets. Now again, I'm not asking my students to do this, but your teacher may ask you to do this if you have a different teacher. So, because I'm putting this on YouTube. Also, it may even be split into a triplet of quartets. Okay, so it could be either way depending on which coupling constant is larger. Okay, so here's an example of the tripling quartet, a triplet of quartets. It just depends on which coupling constant is larger. And if you don't have a good instrument, you may just see a blob, like that multiplet there. Okay, so it's just going to depend. And so here we would have, if you're going across a double bond, you may have widely different coupling constants than across single bonds. And so this is going to be like a doublet of doublets, but they may be very far apart. Okay, so let's see, HA is going to be just a doublet because this carbon has what? They're not doing a very good job of demonstrating this. HA, these are all HA here. Okay, they're a doublet because they're split by HB. HB is split into, it's supposed to be split into a quartet by these three, so I think there's an error here, and a doublet by HC. So either a doublet of quartet or a quartet of doublets. HC is going to be a doublet of doublets split by each of these. HD is going to be a doublet of quartets because there's 3 hydrogens here. And HE is going to be split as a doublet by HD. Okay. HF doesn't split because hydrogens that are on oxygens generally don't split because they don't split through the oxygen, because that hydrogen is exchangeable and it exchanges at such a fast rate. Remember, oxygen alcohol is a little bit acidic and exchanges at such a fast rate that they don't actually split. Okay, so if you can remove all the acid and put it in a very non-protic solvent, sometimes you can get some splitting or even a very sharp peak. But because of this exchange here, you're not going to see splitting across the oxygen. And so you have hydrogen bonding or exchange, which occurs in alcohols, in acids, and in amines. And all of these will give you usually kind of a broad signal. If they're sharp, they may be sharper in a non-protic solvent, but at any rate, they generally don't split across that atom that's connected to them. All right, and so we could determine the difference between, say, these guys on the benzene ring. Okay, so these hydrogens, let's call the blue HA and the yellow HB. So HBs don't split each other because they're equivalent due to this mirror plane, but HB is going to be split by HA into a doublet, okay? So we're going to have a doublet for both HBs, and HA is going to be split into a doublet by HB, so we're going to have a doublet for both HAs, okay? So we're going to have 2 doublets in the 7 region for this benzene ring, and then we're going to have a singlet for those 3 hydrogens. So we're going to have 6 hydrogens as a singlet for those methyl groups. All right, next we've got HA in blue. They're equivalent because of this mirror plane here. H, say B versus C, are different from each other. So HAs are going to be split into a doublet by HC. HC is going to be split into a triplet by HAs, okay? HB is a singlet. And so we can notice that in the aromatic region if we can get good resolution. On this last one, we've got a mirror plane or an axis of rotation to where all of these blue hydrogens are equivalent to each other, so we're only going to have 1 peak representing 4 hydrogens. So we could use NMR to distinguish between these molecules. So for these, we have a similar situation. We have a plane of symmetry here. So these 4 hydrogens are actually equivalent to each other. So we'd see 1 signal for them. And these hydrogens here are not equivalent to each other. So we're going to see 2 signals. So HAs are equivalent to each other. HBs are equivalent to each other. But HA is not equivalent to HB. So we're going to see 2 signals for those. And of course, we'll have additional signals for the hydrogens on the benzene ring. And so you could distinguish against having 2 alkyl signals versus 1 alkyl signal here. For problem set B, we have a CH3 that's next to an oxygen versus a CH3 next to an aldehyde, which is going to be at around 2.5 versus a little higher up, next to an ester, I'm sorry, around 4, I think. So you could distinguish those that way. All right, so the next step is going to be analyzing an NMR spectrum, which we've kind of done in we did that along the way. We analyzed some NMR spectra, but the first thing we're going to do is calculate the degrees of unsaturation given the molecular formula, consider the number of signals, analyze each signal, and put together the fragments into a complete puzzle. So these are kind of like working puzzles, okay? So let's see if we can analyze this spectrum, okay? So notice here that we have a peak at around 10, and what did we say that was? That's usually an aldehyde. That's the first thing that jumps out at me with this spectrum. Our molecular formula is C9H10O. We've got a multiplet at around 7, and then we have these peaks at around 3. So let's see what we have. So our integration is going to tell us we've got 10 divided by 10 is going to give us 1. 54 divided by 10 is like 5.3. 21 divided by 10 is about 2. And then again, this signal is about 2 hydrogens. So we've got 1 hydrogen, 5 hydrogens, 2 hydrogens, and 2 hydrogens. So what can we learn from that? Probably an aldehyde. Mono-substituted benzene ring because it's in the 7 region. Okay, and then we've got CH2 and a CH2. So let's see what we can get from that, all the pieces that we have. Can we put these pieces together to give us a molecule? Well, if we just connect those pieces together, we can actually get a reasonable molecule. Oh, we didn't calculate degrees of unsaturation, because this aldehyde is an N piece. And if we look at the degrees of unsaturation here, remember the formula for an alkane is C sub N H sub 2N plus 2. That would be a saturated alkane. So C9 would be C9H, 2 times 9 is 18 plus 2 is 20. And 20 minus 10 is 10 divided by 2 is equal to 5. So we have 5 degrees of unsaturation. So 4 is taken up by the benzene ring because that's 3 double bonds plus a ring. So that's 4 degrees of unsaturation. And then our aldehyde is 5. So that fits our spectrum nicely. Okay. So let's go ahead and propose a structure for this next molecule. Yeah, this is a different one. Okay. So let's do this next one. So we've got 45, 18, 19, and 9. That gives us a 5. If we divide everything by 9, a 5 to 2 to 2 to 1 ratio. So I divided 45, 18, 19, and 9 by 9, and I got those ratios. Okay. C8H10O gives us 4 degrees of unsaturation because 8 times 2 is 16. Plus 2 is 18. 18 minus 10 is 8 divided by 2 is 4. That gives us 4 degrees of unsaturation, and that's probably associated with our benzene ring, and that's pretty obvious because we have 5 hydrogens in the aromatic region. Okay? All right, and so then we also have 2 hydrogens. That is a triplet at 4 ppm. Now, what I recommend doing if you're working these problems is make a chart. So we're going to say like the number of signals and the chemical shift in ppm, and then the number of hydrogens, and then how many neighbors does it have. And that'll help us put our pieces together. So always make your chart. So, in the aromatic region at 7 ppm, we've got a multiplet that's associated with 5 hydrogens, and those are on a benzene ring, so I'm going to scratch out the number of neighbors. We got this piece right here. Then at 3.8, okay, we've got 2 hydrogens that are a triplet, okay, and so what does that mean? It means they have 2 neighbors. Then at about 2.8, we've got 2 hydrogens that I think are a triplet, meaning they have 2 neighbors. And then at about 2, we have 1 hydrogen at about 2 ppm. We've got 1 hydrogen that's a singlet, meaning it has 0 neighbors. So what does that mean? We've got a CH2 and a CH2, and then just a hydrogen that's by itself. So we'll probably get a little bit of information if we look at the molecular formula, because if we say C8H10O, then we've got 6 carbons and 5 hydrogens in the benzene ring. Okay, so we've used 6 carbons, that leaves us with 2, and 5 hydrogens, that leaves us with 5, okay, and an oxygen. Okay, so now let's go to our next piece. We've got a CH2 we determined and a CH2, so those guys are probably connected to each other because they're each a triplet, and so that's 4 hydrogens, and that leaves us just with an OH. So that last hydrogen has to be on an oxygen. So this would be our molecule. Okay, so the next one, we've got C7H14O, and we don't have anything in the aromatic region. This one goes to 1 to 3.5. So let's get our degrees of unsaturation. C7H14O. 7 times 2 is 14, plus 2 is 16. Okay, so that would be C7H16 if it's fully saturated, meaning that we're missing 2 hydrogens. 2 divided by 2 is 1, so we have 1 degree of unsaturation. Okay, so let's look at our chemical shifts here at about 2 point, let's say 8. We've got a 1, 2, 3, 4, 5, 6, 7 peaks. Okay, and at about 1, we've got 2 peaks. Okay, and let's get our integration here. 10 divided by 10 is equal to 1, and 65 divided by 10, 65.7, it's about 6, right? It's not quite 6, but it's about 6. So our ratio is about 1 to 6, okay? So this guy is associated with 1 hydrogen, this one is associated with 6 hydrogens. And so what does that mean? So our molecular formula is C7H14O. Okay, so that's kind of confusing, right? So if we had, this looks like an isopropyl group, right? Okay, so that's 6 hydrogens, 6 plus 1 is 7 hydrogens, and 3 carbons. Okay, so we got to have something here. We got to have a lot of symmetry because we've got to have more carbons and hydrogens. So if we had these 2 pieces, that would give us some symmetry. That's 6 carbons and 14 hydrogens, right? So the only thing we're left with is a carbon and an oxygen. So we could put that right into the center, and that's our molecule. Okay. All right, I'm going to work one more before I quit for today. Here we have this spectrum, and we have C10H14O. Notice this broad peak here at 5 ppm. So at 5 ppm, we've got a singlet with 1 hydrogen. Okay, we've already got our integration values here. At 7.2 or so, we've got a doublet representing 2 hydrogens. Okay, so this 1 hydrogen has 0 neighbors, or it's so broad, it's probably an OH. It looks a lot like an OH. At 7.2, we have a doublet. We have 2 hydrogens. That means they have 2 neighbors. And at about 6.8, we have a doublet. That's 2 hydrogens with 2 neighbors. That means we have, for this aromatic region, notice it's around 7, we've got 2 sets of 2 equivalent hydrogens. That means we have a di-substituted, an equally di-substituted, or a di-substituted benzene ring, right? Now, at about 1.3 ppm, we've got a singlet representing 9 hydrogens. Now, what does that look like? That has 0 neighbors. 9 hydrogens is what? That's very characteristic for a T-butyl group. Now let's add up our pieces, okay? So this T-butyl group is an end piece. This looks a lot like an OH, but we're going to examine that more in just a minute. And that's also an end piece. And this benzene ring is a middle piece. So could we take this T-butyl and stick it maybe here? And then take this OH and stick it maybe here and have our molecule? Let's look at our molecular formula. I forgot to do degrees of unsaturation. So C10H14O gives us 4 degrees of unsaturation because our alkane formula is C sub n, H sub 2n plus 2. That would be C10H22 is fully saturated, and 22 minus 14 is 8, divided by 2 is equal to 4. So that gives us 4 DU. Okay, so let's also look at our formula. So I'm going to mark this in a different color. These X's, these are X's saying there's nothing there right now. So this is, this benzene ring takes up C6H4. This, and we don't really know about the OH yet, so let's just leave that out. This T-butyl group takes up C4H9. So when we add those together, C6H4, that's H13 plus C10. So the only thing we have left is an OH from our formula here, C10H14O. So that's definitely going to be an OH. So this is actually our molecule. Let me erase all this, okay, and get another color here. This is an OH, and this is a T-butyl group. And that is how we will determine our structure. Okay, and that's our structure. We're going to do just one more, I think, for today, and then I'm going to stop. This one has C9H10O, and see this in the aromatic region. So 9 times 2 is 18, plus 2 is 20. So that would be, H20. C9H20. 20 minus 10 is 10, divided by 2 is 5, so we got 5 degrees of unsaturation here. All right, so that means we have a benzene ring. That's going to take up 4 degrees of unsaturation, okay? What about our integration values? If we divide everything by 13.9, that's going to give us a 1 to 1.5 to 1 to 1.5 ratio, and we can't have that, so we have to double it, 2 to 3 to 2 to 3. So what does that say about our benzene ring? We got a 2 and a 3 here. So this is a doublet and a multiplet. I don't know if we can make any sense out of that, but that means that we have 5 things on that benzene ring. We got 5 hydrogens, and so it really doesn't matter. It's a monosubstituted benzene ring. Okay, and so at 7 ppm, we've got a multiplet representing 3 hydrogens. Again, that's part of our benzene ring. At 8 ppm, we've got a doublet representing 2 hydrogens, okay? At 3 ppm, we've got a quartet representing 2 hydrogens. And at 1.3, we've got a triplet representing 3 hydrogens. So we're not going to worry about this. This is a benzene ring. At 3 ppm, we got a quartet representing 2 hydrogens, so they have 3 neighbors. At 1.3, we have a triplet representing 3 hydrogens, so they have 2 neighbors. What does that mean? We got a CH2, CH3. These guys are connected together, so they're coupled together. All right, so what does that mean? So we've got C6H5 in this benzene ring, and now we've got C2H5 with the ethyl group, so that's going to be C8H10. So what do we have left out here? We've got a carbon and an oxygen left. Okay, so what does that mean? That means we've got an ethyl group and we've got a carbonyl. Okay, we got an ethyl group. We don't have any hydrogens left. That is very interesting. Oh, I see. So we've got a carbonyl. So we got a ketone. CH2, CH3. And then we got a benzene ring over here. Okay, so that's all we're going to talk about for today. That's all we're going to talk about for today. So this is our molecule. And next time we're going to talk about carbon-13, and we're going to put this all together with some integrated spectra. So I'll see you next time. Thanks for watching.